I want to start thanking Vale do Rio Doce for making this possible. And I'm going to invite Rubens and then Castello to speak, and then I make a formal introduction to Professor Lucas, as you all know, will be our guest today, and I have a great honor to have him.
Thank you, Aloysio. Good morning, everyone. It's unnecessary to say how pleased and how delighted we are to have John Dewey, Distinguished Professor of the University of Chicago, Robert Lucas, with us today here. And we have actually two reasons, at least, to commemorate this special occasion. First one is having this speech by Professor Lucas, which is important not only by its content, by what he's going to show to us, but also as a kind of rite of passage for the end of this year and for having the students having their mind turned to the important subject of economic development and economic growth. And the second reason we have to commemorate is that we have just been appointed by our Ministry of Education as having maximum degrees in all our programs. Undergraduate, maximum degree 5. Master of Finance, Professional Master of Finance, maximum degree 5. Academic Master, maximum degree 5. Doctorate, maximum degree 5. And ranking first in the Tilburg ranking of economics in Latin America somehow provides robustness to these domestic results. All the results put together means that in the last 4 years, 3 times we have been pointed out as first institution of higher education in Brazil among 2,178 institutions, and the 4th time as second among all these institutions. Of course, all these measurements are subject to error and are just a tiny portion of our great mission, which is developing ideas, sustainability for economic development in Brazil, the best possible teaching in economics, and that's our main purpose. But of course, none of these achievements would have been possible had we not counted with the work of several people who I can see here. In the undergraduate course, I'd like to mention the work of Renato Fragelli Cardoso and Afonso Arino de Melo Franco, Luiz Bertolino Braido, and André Vilela, who have kept all these years since its inception maximum degree in all evaluations. Regarding the Master in Finance, I'd like to mention the work of Professor Pedro Cavalcante, who is with here us today, Professor Marco Bonomo, Professor Ricardo Cavalcante, and Professor Joísa Dutra and Teresa Duclos. And last, regarding our Master and our Doctorate, academic ones, Professor Carlos Ellery and Professor Humberto Ataíde Moreira. I'd also like to mention the work of the 2 professors who are sitting here with me at this table today. Professor Castelo Branco has been very, very kind with our school. He's the first graduate in our doctorate in, I don't remember the year, Castelo, but it has been recently soon. It's okay, yeah. And he has been very kind by being with us not only in this day, but also in many other occasions, and have provided help to us through Vale. And I also like to thank Aloysio Araújo. Aloysio Araújo not only has had the most prestigious positions in the international academia, published in the most important journals. But that I think that is a tiny fraction of his greatest work, which is to have forged several generations of top leading scientists and economists in Brazil. I'd like to take advantage of this occasion to ask that you clap your hands for Professor Aloysio. Work well done. Thank you.
Thank you. Thank you. That's quite unexpected. Thank you very much. But Roberto, please.
Good morning. First of all, I'd like to congratulate the faculty for these great achievements, and thanks Aloysio for the partnership in this event. Vale is a mining company, and mining, despite opinions in contrary, is a knowledge-based industry. It requires a substantial amount of accumulated knowledge in geology, mining, economics, and finance in order to thrive in a fast-changing global economy. It's a highly capital-intensive business in physical capital as well as in human capital. And learning through the experience of others is very important to us. So the interaction with the academic world is of paramount importance. To us, it's a great pleasure to have helped the Graduate School of Economics to invite Professor Robert Lucas, who, in my opinion, my humble opinion, is one of the three greatest economists of the last, at least of the last 100 years, jointly with Professors Milton Friedman and Gary Becker. Thank you.
Okay, now make a brief introduction to Professor Lucas. Is along the lines of Roberto, no? I agree with him. Lucas is just one of the greatest economists in the 20th century. And in 21st, still doing very good work. And there are very few economists that could be associated the name of revolution with it, no? And Lucas was the leader of the neoclassical revolution. Macroeconomics was disassociated with micro. There are two different fields before Lucas. And then everybody was uneasy about it. Not everybody, but many people. Disaggregate things, just look in the economy in this way. It could not work. There are some rational people around. And then, but there are few people that wanted to do that, was aware of this problem. And, but Lucas was the one that did it. And he and a group, Prescott, Sargent, Hansen, that got the Nobel Prize recently. So Lucas is much more than a Nobel Prize winner. He is a person that created a new paradigm, put economics back together again. And we should all thank for him. It's true that I learned this thing from him while I was in Chicago. I taught a little bit there, a couple of years, in the late 70s. And then we learned that rational expectations and how important to fiscal deficits are important for inflation and so forth. Coming back to Brazil in the 80s, then I saw this. It looked like the Brazilian economy didn't know anything about it. So they start price freeze after price freeze, and then price freeze. So it was, in some sense, uneasy for me to look at these people and then And then think about Lucas, the rational expectation. So the 10th time that they're going to do price freeze, not going to work. People anticipate it, and that was it. At some point, one of these guys that were associated with this price freeze had lunch with another one, and then supermarket the next day could jack up the prices. So, and people complain about it. So when you have rational, you think in macroeconomics that rational agents on it, makes a huge difference. Perhaps you cannot find the truth immediately, but you can avoid lots of mistakes. And that's all due to Lucas. Besides this revolution macroeconomics, the neoclassical revolution, it was very important also in economic growth, asset pricing, and more recently he is involved in international trade, those beautiful things in international trade, and cities and knowledge. That's the subject he's going to talk about today. I'm not going to steal any more time of his. I'm sure you prefer to hear him than me. So I just invite him to speak. Thank you for coming, Bob Lucas.
I'm going to talk about a line of research that I'm engaged in now about economic growth. And I'll put a lot of equations on the blackboard or on the slides and talk about them, because the way I like to think about economics is to take simple models that capture a few forces that I think are important for certain questions, and take these models as serious sort of analogs to what's going on in the real world, and that involves testing the models against actual data. And I haven't got as far as, don't get your hopes up too high, I haven't gotten as far as I'd like to, but I'd like to talk about it. The particular feature I want to talk about in economic growth, if you've had any courses in economic growth at all, you know that the main driver is increases in knowledge. We produce more than we did 100 years ago because we know more things that people 100 years ago didn't know. So it comes down, now of course additional capital, these kinds of things are also help, but the main driver of economic growth is improvements in knowledge. You can use many terms, technology, human capital, they're all kind of the same thing. We produce more because we know more. And the feature of this is a fact that I don't think anyone would dispute. The feature of learning that I want to focus on is the social character of learning. That you know from your own experience that you learn what you learn doesn't depend entirely on what you do by yourself. It has to do with the people you're talking to, the people you're arguing with, the people your teachers. But as you get old enough, so you're one of the teachers, you're learning from your students. So when I think about what I know in economics now versus what I knew when I got my degree in 1963, I mean, I didn't know anything then. Now, by current standards, so much has happened in my field, and I've interacted with so many first-class people, and you know, that's been my life. And if you sort of put me on a mountaintop somewhere and left me alone, I don't think I could have done anything. That's not the way human thought involves interactions with other people. Now, and this is something that growth theorists have not really dealt with, and I think we should. So that's what I'm going to be talking about today. Now, one of the reasons it matters is, you guys know about external effects. I mean, if what I'm saying is true, then when I learn something new, I get a salary increase, and I get a return for it in the sense of higher earnings, but I don't get any return from the fact that my knowledge benefits other people, So there's an external effect, and nor do I have to give any return to all the people that have helped me learn. So there's a social benefit to learning which exceeds the private returns. So I think this is exactly why governments in any reasonable country are involved in schooling, and people recognize this. If you look at histories of, let's see, I've got to be turning this page here. I haven't been trained for this. There we go. I'm sorry. So if you look at the history of arts or music or science, business, sports, they're all when you get into all these things, you're talking about influences people have on other people, how you're learning from other people in your field, I think back to Arrow's 1962 paper on learning by doing. It's got a feature that when somebody does something innovative, that enables other people to do something innovative. It's got this external effect that I'm talking about. There's a paper by Nancy Stokey in 1988 that has that. If you interpret Romer's 1986 paper or my 1988 paper, if you interpret those generously, we're talking about social learning. But I want to get more specific about how social learning works in this talk. Now, what I'm doing is sort of an amalgam of work that I've been doing. I'm going to take pieces of my talk from other papers, and I'll just list them here for completeness. I worked with Fernando Alvarez and Francisco Buera in a couple of papers, and Benjamin Maul and I have done some work together. So the work I'm talking about here, of course, we're drawing on all kinds of other people. That's the whole theme of my talk. But in particular, what I'm talking about is work that I and collaborators have done. So what's the plan? I'm going to take a very simple model, the simplest model I can think of growth that's driven by learning from other people. And it's just going to be some math. I'm going to set it out and work out its properties. Then I'm going to claim that this model lets us think about some evidence on individual earnings. And then we're going to look at match up the model with some data and see how well to what extent that's true. I think it's going to look pretty cool. On the other hand, there's a lot of things that it could make it look even better, so we'll see. In these models, people just go to work all day and stuff happens. No one makes any choices about how much time to spend learning versus how much time to spend producing with what they already know. And that's obviously leaving out a lot. So this third thing I'm going to talk about is a continuum, a model in which you got to allocate your time between producing and learning. You can't do both, and then you got a choice to make about how to split your time, and that involves a control problem, a Bellman equation. Changes the whole thing. And then the final thing, if we have any time, is to talk about an extension to trade theory. I have to shuffle these papers because I don't want to turn around for everything I say. So I've told you what I'm trying to think about, and what I want to do then is to put that down in some mathematical model that I can actually work out. So it's going to be simple. It's going to be super simple. We can talk maybe a little bit later about how we might want to complicate it. The basic ideas in the math I'm going to talk about is an equation that Sam Cordham introduced in 1997, and then he and Jonathan Eaton have applied it later on. What I'm going to be doing is based on their work. So I want to describe an economy. And I'll tell you every detail. The whole beauty of theory is you know everything because you're making it up as you go. Okay, so here's an economy with a continuum of people, continuum of agents. I'm going to have a mass of 1. And everybody's got 1 unit of labor time, and that's the only factor of production. So they're people, they work, they produce. And right now I'm going to think of them all as producing the same single good. I want to keep things simple, as I said. And this is going to be so I'm just going to call the production GDP, and then my individual production is per capita GDP or per person GDP. Now, these people are going to differ in how productive they are. And I'm going to think of them as a draw. Each person has a productivity level which he draws. You can think of it as a draw from some probability distribution. I'm sorry, the probability distribution. I'll call that the CDF F of ZT. That's the probability that a person selected at random at time t has a productivity less than z. That's capital F, and then I'll call it density little f. So I'm just describing the people in this world. I'm not going to give them names or anything. Just think of them as Z. That's all we need to know about you. And in this model, and this is going to be, it's going to hurt, but I got to say it. You're producing, people aren't cooperating to produce something. There's no team effort in this world. Everyone's on his own. You got your Z, you produce Z, that's it. And then what's the total production in the economy? We'll just add up. We'll just add up overall, or in this case, integrate up over all the people in the economy. The density function is little f. F of ZT produces Z at day t. And the total, that integral is just the per capita income, per capita production, per capita GDP in the economy. So that's it. And the whole theme then is going to be, how do these individual, I'm going to have a model for how do people learn, or how does this distribution evolve over time. And this is what I take from Cordham, okay? And here's the idea. Let's take an individual at day t and look at what happens to him between t and t plus h. Now, in that, I'm going to assume that people are getting continuous draws from a distribution that's built on this f. But notice that it's f to the power alpha times h. So the distribution gets worse that you're drawing from, the smaller is h. So in some sense, the more you draw, the better off you are. You might think of writing this in terms of Poisson arrivals, where either get 1 draw or 0 draws from the original distribution f. But for my purposes, this continuous draws idea is a real simplifier. And what happens when you make a draw? Okay, I'm Z. I meet somebody who's got productivity Z prime. Now I get to choose. Do I want to keep my own Z, or do I want to jump to his Z prime? Well, of course, if his is better, I want to switch. So every meeting, I can ignore the guy I meet if he's worse than I am, and if he knows more than I do, then I'll upgrade my knowledge. So this bumping in, people are bumping into each other at random, and it's a way where they're always getting better, or at least no worse. So I said I wanted a model of growth. I'm building that right in. All right, so what's the probability that I'm going to still be productivity less than Z at T plus H? Well, the only way I could be in that situation is, first of all, I got to be less than Z in productivity at date T, because you never go backwards in this economy. So the probability I'm still below Z at T plus H is equal to F of Z times the probability that the draws I get in this interval, none of them is big enough to upgrade me. And that's a little f of Z T to the power alpha H. So if I subtract f of ZT from both sides and divide through by H and take the limit as H goes to 0, I get this differential equation that I call dE. And it's just the derivative of the log of f equal alpha times the current log of f. So it's just a first order linear differential equation. We can just fix Z and just solve that. For each separate Z, we can treat this thing as a first order equation in f. And this is a famous, so we can just write out the solution. It's just the log of f of zt at any future date t is the log of f of z of 0, the initial distribution, to the power e to the alpha t. And you'll notice that the distribution, you're putting probability mass is always increasing, or at least not decreasing. So it's a model. I said I wanted a model of growth, and we got one. Now, there's a problem. Everything depends, every idea that anyone's ever going to have in this world is got to be already present, because you're only meeting from people to find out what they already know. So you got to have, so the question is, what if you kind of run through all the good ideas, the economy is going to bog down. No one goes backwards, so you'd always be growing, but you might have some limit on how much you can get. Now, this troubles some people, but it doesn't trouble me very much, so I'm going to go with this anyway. But because we know that a theory of growth is going to have the property that you don't run out of ideas. I mean, nobody knows nobody really knows that this learning can go on forever. Bob Gordon at Northwestern thinks all the good ideas have already been produced, but I think it's just he's old and tired. That's not his interpretation. But I'm interested in sustained growth. What you see when you observe the successful economies in this world and some of the unsuccessful ones is pretty stable growth. Like per capita income in the United States over the long haul grows at about 2% a year. And that's been going on for a century and a half. Now, of course, if you go back to the birth of the Industrial Revolution, that wasn't true. So, and maybe it's going to end someday. But for a model that fits the last couple of centuries, I don't want a model where it predicts that growth is going to peter out. I want it to maintain stable growth at 2%. And that involves what we call a balanced growth path. We want to ask, does this differential equation of ours have a solution which is consistent with stable, constant rate of growth over the time? Of course, that's going to depend on the initial conditions. So the question we could say is, could we find constraints on the initial distribution of knowledge, which will be consistent with a constant positive growth rate? Now I seek that because to me, it's a main feature of the economies I'm trying to understand. It's an empirical motive. And the answer, I don't know how much I should get into this, but the answer is there's only exactly one distribution which is consistent, initial distribution, which is going to give us a balanced growth path. And it turns out that's a Fréchet distribution. And let me just show you a picture of what a Fréchet density looks like. Okay. Frichet distribution, how do you get, well, it's a two-parameter distribution. Maybe I'll go back. Lambda is kind of it's the thing that grows over time, and theta is a sort of like a variance or a tail parameter. I'll tell you what theta is important. Theta is a constant over time, and the growth in the system is going to be boiled down to a growth in the single parameter lambda. So here's the top. Here's the density. Theta is equal to 1/2. It's got to be between 0 and 1 to make things converge. So I'll show you where I got 1/2 later on. And then lambda is growing 2, 4, 8, 16. So each of these curves is doubling. You're doubling the position parameter, kind of the mean. If you take logs, which means once you take logs of productivities, they don't integrate to 1, but you can see that the log variances, the relative variances on this balanced growth path are constant. So we got a model in which relative earnings is constant over time, the growth rate is constant over time. And, well, here's just a picture of some, let me go back a step. These are pictures of the distribution that describes the whole economy, everybody in the economy. How about a picture of some individual careers, individual people? These are just random. You can generate. I could, generate careers on the computer at will. Here's 3 people. They start out with nothing. They know nothing. They bump into somebody. Of course they take that because anything, nowhere to go but up when you start, and then you go with what you got until you meet somebody else and it bumps up. So see this red curve here. He got off to a super start, but then he kind of, that was it for him. The green guy took a while, but he ended up passing. It's everybody's proceeding by, when they hit a lucky draw, they jump to a new level, and the career is an upward climb like that. Okay. We got a little theorem here that says that well, if theta were equal, think about theta. If theta were equal to 0, theta is kind of the variance of these things. If theta were equal to 0, everybody knows the same as everybody else. But the only way we learn is by bumping into other people. So if there wasn't diversity in this economy, all this bumping into people would be nothing. You'd just be meeting people who are exactly like you already are. So theta, more variability there is, the better. If you got a big right tail, then you might meet somebody really smart, and that's good. And if you got somebody who's really dumb, well, you can ignore them. So it's a can't-lose situation. The more variance you have, the better off it is. So this parameter theta is crucial. And do I have a picture on this? No. You got to have a fat tail in the distribution. You got to have enough good ideas out there, and they have to be out there from time 0 in order to keep this system going forever. So the Pareto distribution's got that property, and this Frichet distribution, as do many others, has a tail that looks just like a right tail that looks like a Pareto. So that's the map. And that's the only distribution that's going to generate this stable growth. All right. So on a balanced growth path, we've got that formula, and then we integrate across all the people in the economy, take into account that F is going to follow this Fréchet distribution. Then the growth rate of the economy is the product alpha times theta. Alpha is how hard you search, how often you meet people. That's your part of the job. And theta is the diversity parameter that describes the people you're going to bump into. And the growth rate of the system, the thing I call 0.02 in the U.S. economy, is going to have to be equal to alpha times theta. So this captures what I started out by talking about. And since we want to talk about social learning, that's it. That the rate of growth, it depends on individual efforts and on the diversity in the economy. Now, is this thing, this model's pretty simple, isn't it? And does it just imply that there's nothing going on but imitation, and there's no innovation? That's just wordplay. The math is what does it mean to me? Means that you might read an article by somebody that stimulates you. You see a TV program that gets you going. You had a conversation with somebody. You bought a product from somebody or saw, any of these stimuli can help you solve some kind of problem. That's everyday life, isn't it? And I'm lumping it all down into this plain vanilla, everybody's a draw, it's common distribution, because I want to do something that I can solve, and it worked. I solved it. And I can solve this particular model. So that's a model of sustained growth which has this social learning. Now the next question I want to ask is, the model works exactly the way Solow's model in 1956, who started all this growth theory for us, worked. So have we made any progress since 1956? Well, this model, unlike Solow's model, it has predictions about individual behavior, individual careers. So we got data on individual careers, tons of it. So why don't we take some of these predictions about earnings, some data on earnings, and match it up with what the model would predict, and see how well it fits. So I want to do that next. And what I'm going to use are these. Every country's got these. This is U.S. Census cross-section data. So every 10 years, you're getting data on people's age, their earnings, and a lot of other stuff. How much schooling they had, whether they're men or women, whether they're black or white. The census asks a whole bunch of questions. And all this stuff is for the whole U.S. society is compiled every 10 years. I'm going to work with the 1990 U.S. Census data. They all look pretty similar. So I just want to show you the data that I want to be talking about. So this now, each dot here, these are classified as white male heads of household. I don't know why. I'd like to sort of lump people together in a reasonable way, because but I didn't do it yet. And they're also stratified by schooling levels, which is hugely important, but I'm not really talking about schooling in this talk at all. So like the red dot are college graduates. Everything's in 1990, and then their age in the year 1990 is on the horizontal axis, and the log. Okay, so each of those dots has thousands of people in it. We're counting up everybody in the country in there. Everybody's. I'm in there. Maybe we see as we're counting, or we count people who are employed, whether they're U.S. citizens or not. So we're all there, and what I've got here is the mean of the log in each cell. I got the whole distribution. In fact, I could look at the distribution and see if it's really a Fréchet. Each one of these little cells has got a distribution. I'm going to look at the means and the variances today. And these dots are the means. And then so this is the mean. The vertical axis is mean log earnings, annual earnings. Okay, now, so I'm going to match this. Now, these guys grew up to 90 years old, and the 90-year-olds are already contributing a lot to production in the U.S. economy. See, I just want to cut off, I'm going to cut off all the dots past 60. You know, we could have a theory of retirement, but I don't. So since I'm trying to, I know what my theory can do and what it can't do, and it doesn't have anything to say about retirement. So if you're not 60 years old, you know, I'm cutting you off. Let me see. So the data that we're actually going to fit the curve to is that. Those are the same dots you saw before, but I chopped off the old guys. And maybe some of the young guys, okay? And in fact, what I'm going to be doing when I test the model is to think about a pseudo economy where everyone is either on the red dots or the green dots or the blue dots. I'm not going to think about people at different schooling levels interacting. Of course, I'd love to do it, but I'm trying to keep things simple enough so I can get somewhere. Okay. So I'm going to go back to the theory and see what it says those curves should look like. But I got to do a little more work, because in the model everybody lived forever. In the model I gave you before, and nobody ever dies. And you know, the whole census stuff is a chapter of life cycles. You got to replenish your labor force with new people, and the old guys retire. So we got to have a cohort structure. We got to change the model to take into account that people are different ages if we're going to fit that data. So I'm going to keep the demography fixed. There's a given distribution of ages, just depending on births and deaths, and the density function is little pi, and the cumulative distribution function is capital Pi, and there's no t in there because this demography is constant. I'm not trying to capture, well, I'm not trying to capture population growth here, although it's interesting. And in particular, I'm not counting immigration, which is huge for the United States. But right now, I'm not dealing with that, and I'm also not really dealing with the schooling issue. The choice of schooling issues. So everyone in this world now, you get born at age 20, you know, and you start working right away, and you keep going until your number is up, and then you die or retire. And I'm going to have the retirement. I'm really going to have a rectangular distribution of life cycles. So people are going to work, and then it's over at one. So what do you do? Well, it's just like you did before. You keep meeting people. Your productivity evolves over time, and you keep going. No choices to be made here, really. All right. Now I'm going to assume, again, that the entire economy, if you're drawing at random from everybody in the entire economy, like we did before, that you're drawing from a Fréchet distribution like we did before. The drawing's more complicated because now people differ by ages, but you're going to draw in proportion to how likely each, how many people are in each age group. And then I want to have a separate distribution for this within cells. So I want to call that mu of st is the lambda parameter. It's for people of age s at date t. So they were born at date t minus s. Now, I'm not going to work out the math here. Well, the second equation says that lambda, the economy-wide parameter, is just all the cells integrated with respect to the density S. You're going to add up all the people in different age groups, pi of S, associated with each group, its parameter, mu st, and that's going to be lambda t. So now on this page, wait a minute, what am I doing? Well, we got mu depending on lambda, because you're learning of a guy of age S is, he's been meeting people in the economy between t minus s and t. So he's learning from the people that he meets, and then you get a. I'm being clumsy here. This economy-wide knowledge really affects everybody's learning, and everybody's learning, in effect, determines the economy-wide average. So we can just eliminate this mu, and we got a new equation at the bottom of the board in lambda, which is what's the this go. Now I'm going to assume we're on a balanced growth path. So lambda, which it comes, you can see it on the left and the right hand side of that equation. There's the same equation here. On a balanced growth path, lambda is just some constant, call it b, times e to the gamma t. I don't know what gamma is, but I'm seeking a constant growth rate. So I make the substitution for lambda, cancel out the b's, cancel out the e to the gammas, rearrange, and I get that equation I call star. So the gamma, which is going to govern the growth rate of this economy, I got to solve an equation, but it's one equation and one unknown. You can see if you look at the equations that 0 is always the solution. You get a concave. This is the fixed point problem. If you're learning fast enough, that's the red curve. If you get a high enough alpha, then the growth rate is going to be determined by, you're going to have an intersection to the right of 0. If you're learning too slow, like alpha, if your learning rate is too slow, your economy is not going to grow at all. It's not going to go back to negative growth, so it's just going to be at 0. Now what's going on here? This is not a feature that was in the earlier model. In this model, you've got to keep replenishing your knowledge. You're getting people are learning, they're getting older, but then they die off, and you're going to replace them with newborns who don't know anything. So there's a depreciation in knowledge that goes on in this world. Now you could say, well, if we had capital or books or something like that, that would help us. But there's a depreciation factor here that's not true in the original model. Maybe I'll just let that be. I kind of like talking about this stuff, but it's maybe I shouldn't go into too much detail. All right, now this model, it's a Frichet model, it's a balanced growth path model, it's a model with a fixed demography. We can calculate what the variance of what the mean of the log of earnings is in every cell in my fictional economy. We can just work it out. And there it is. It's WST is the log of earnings of people of age S at day T. Those are the guys I'm. And we can also get the variance of the log of earnings, which is just depends on the parameter theta. That's why I call theta a variance parameter. We could get the whole distribution and see if it's Fréchet, which I've started to do, but I'm not going to talk about that here. So now we can start to estimate some of these parameters. If this model were now, as I say, the growth rate in the system, it's gamma. It used to be alpha. Theta used to be the growth rate of the system, but now because of this deaths and replacements, it's this parameter gamma that we just solved for. So gamma times theta is the growth rate of the system, and that thing's about 0.02 in the United States. So we can't estimate either rho or gamma, but we know the product has got to be around 0.02. So that's something. We've estimated one parameter in a sense. Now we also know that the variance of log of earnings is equal to theta squared times, pi squared over 6, which is some number that we know. So the variances within cells, which we can also measure, are estimates of theta. So here they are. For this, now I'm going back to the 1990 data set and pulling out the variances along with the variances, the log of earnings as well as the means. That's this stuff. Now, the theory says that theta is supposed to be constant across life, across everybody. So this thing is supposed to be, these curves are supposed to be flat. Now, for the 5 to 8 year guys, the blue dots, that's pretty close to true. But things get pretty bad as you start adding on education. The green guys are the high school graduates, the red guys are the college graduates, and the variances kind of increase over time for the better educated people. Now, I'm working on that problem right now with Esteban Rossi, but right now I'm just going to pretend that I'm just going to treat theta as a constant and call it 0.6, which kind of hits this average here. See what I'm saying? You got to make some compromises if you're going to be an empirical scientist, and this is my big one. And it's got to be thought about. If you've been paying attention, you see a lot of things I said I'm going to solve some other day, but onward. Oh, sorry, I lost my place. Okay. Other people have noticed this fanning out of earnings over time, and it's a pretty interesting. It comes up in lots of different data sets, so it's not going to go away. It's a problem. But I ended up getting a theta of 0.5, and since I know the product of theta gamma is equal to 0.02, then now I know gamma. So now I got every parameter in implied age earnings profiles is just that bottom formula, and I got numbers for theta and gamma. Okay, so now we got something to compare against the data, and here it is. So the red thing came out of I didn't pick the curves, the curvature or the slope to match up with the dots. I've already picked those from looking at that thing. So now I'm bringing in, the only thing I'm choosing here is how high to start each one of these curves. I got a free parameter for each schooling level. So I pick one that looks pretty good when you start, and it just tracks beautifully, huh? You ever seen anything that cool? In economics, matching of This is real theory now. This is not curve fitting. Okay, I got both parameters estimated, and I went in there, and they pretty much capture the whole show for all these different schooling groups. I'd like to have a theory of schooling too, but be patient. Now, there's a problem at the end of the line there. And a lot of people have noticed, work like by Sherwin Rosen or Jim Heckman, these curves just tail off. The dots, they start to fall off as you get close to retirement. Or maybe some of those guys really have retired. I don't know. But in my model, the red curves are always going to go up. That just comes right out of the math. So there's no way to fit this retirement business. So that's another puzzle that's another issue that has to be dealt with. I lost track of the time. What should I be thinking of? Okay. Okay, I'm going to. I'll go quickly, and then I'd like some time for discussion. I'm sort of going to advertise a couple of papers, and maybe not just explain them in any great detail. So I got a model of a bunch of people who live forever. We got a model of a bunch of people that have, life patterns, births, deaths, learning, retirement, and in compared to that, comparing these to data. So, but nowhere in this model does anyone have any decisions to make. I didn't let them decide how much schooling they wanted. I didn't let them decide when they retire. I didn't, there's, so. Now, economics is all about decisions and, what the consequences are of people's independent decisions, and nobody's making any decisions in this theory. So that's a real, limitation. In some work that Ben Ball and I did, we tried to get around that and add a decision to the model. So I'm going to go back to the infinitely live model, but I'm also going to add, I'm going to say that you can't, in the original model, learning is just a byproduct. You work all day, you bump into people, you learn something. Now you're going to have to choose. You can work you can produce and earn with the knowledge you've already got, or you can search for new, and you can divide your time any way you want. So there's the original model. I'm now going to switch to Poisson arrivals. We did that in this paper. It makes a difference, but let's not talk about it now. It's just math, the economics. So I'm now going to talk about a slightly different equation from DE, which is the one, I call them all DE because they're all differential. I should get a better notation, shouldn't I? But the important difference here is going to be that people divide their time. You can spend a fraction S of your time learning and 1 minus S of producing. So you know what's going to happen. The guys with low productivity are going to want to, their opportunity cost of search is pretty small because they're not very good anyway. So they might as well search. And the people who are really high productivity, they're going to search less. So we're going to have. So I'm going to have alpha is going to depend. Alpha is the rate at which you meet people. Now that depends on how much time you spend trying to meet people, which is your S, and your S in turn depends on your situation. So you've got productivity Z at day T, you're going to choose some S, which is Z and T, which depends on your which determines how hard you search, and then you're going to get alpha of that. Is what you're going to. Now this changes the differential equation. Why? Because now you used to just be looking at the number of people whose productivity is less than or equal to Z, and multiply that by alpha. But now people who are less than, whose productivity is less than or equal to Z, aren't all equally interested in searching. So I got to take the integral from 0 to Z of how hard everybody with Y between 0 and Z, how much they're trying to improve themselves. And that changes the equation that way. And physicists call this thing a Boltzmann equation. There's no choice here now. This is just the dynamics of the evolution of the distribution when people at different levels make different choices. A continuous time Bellman equation, where V of ZT is the present value. These guys are just maximizing the discounted present value of their earnings. And V is the discounted present value of your earnings, if today's date is Z, and your productivity is T, and your productivity is Z. So we get a Bellman equation. And what Maul and I do in our paper is look at, so now we've got two equations and two unknown functions. One of the unknown functions is the distribution. We're going to look at balanced growth paths. Is going to be the distribution F, and the other one is going to be the value function and the policy functions for V and S. And this is really a system of partial differential equations, which I know nothing about. So that's a blow. But you got to be agile. I'm going to find some co-author. If any of you guys is an ace in calculating partial differential equation systems, let me know, and maybe we can make some progress here. All right. I'm just going to show you some. So what we did was we restricted ourselves to BGPs, balanced growth paths, and then we calculated the thing numerically. We can't solve this. We can't write out a formula for this thing, but we have an algorithm that's super fast and easy and accurate. It's just fantastic. So what happens? So here's the policy functions. The productivity is on the this is a balanced growth path now. Productivity is on the x-axis, and the y-axis is the fraction of your time that you spend searching. Okay. So look at the low productivity guys. I had two different parameters stated, but let's just look at the theta equal 0.5. So if you're really low productivity, you spend all your time searching. The opportunity cost is 0. And then as you start to get up to be a certain level, you'll start producing, and by the time you get to the super productivity guys, they're hardly doing any searching at all. I want you to see that the curve, we don't have Frechet distributions anymore, but we can calculate the distributions we've got. It looks pretty Frechet-like in that picture. That's the blue curve. And then the Pareto curve is the green dots, and they coincide for, I said this thing's got to have a Pareto tail, and it does. Okay. We get Lorenz curves in this world because different people are doing different stuff, getting different luck, different earnings levels. So red line is the 45-degree line. The earnings curve in terms of current earnings is the green curve. The farther away the curve is from the red line, the more inequality there is in the society. But the right thing to look at, we think, is the present value of of your earnings. There's a lot of mobility in this society because, you know, if you're low productivity, you're going to search, you're going to find something better. You know, you're not going to be stuck there forever. And you can see that the measured inequality in terms of value learning curve is much better than now this is all extremely interesting to me, but now one of the things we can do here now, we can talk about externalities, because people are making their choices. That Bellman equation, this Bellman equation describes a guy who is thinking of himself and his own earnings only. He cares about nothing about society, okay? Even though that if he would spend more time searching, it benefits society as a whole more than it benefits him because of these external effects. So if we had an idealized economy in this world, a planner would step in and add some incentives for people to search more. And this was really a hard problem, which Ben solved. We can work out the math for the planner's problem, which is not the Bellman equation I just showed you. It's an equation that takes into account the social benefits of search along with the private benefits in just the right way. Now this planner's problem, this is an endogenous growth model. So if the planner runs the show, the equilibrium growth rate in the system is 0.02. I'm treating the existing society as being, I don't know, 0.02. If that were the case, then the planner would induce more search, and it would raise the growth rate to 2.7%. That's a pretty big number. And that's in some sense the measure of the external effect here. Now, in fact, learning is subsidized pretty heavily within the United States economy, so maybe we should have calibrated the planner's thing. You know, I'm not quite sure how close to the planner we are in actual. But you do see this tension between social and private returns here in a nice way. In terms of the income Lorenz curves, looks like in order to get this higher growth rate, the planner is forcing a lot more inequality on the system. But if you look at the value Lorenz curves, it's only the very high productivity people who were affected by that, and the rest of the inequality, the two curves, the equilibrium, the solid blue curve, and the green dots are pretty close to one another. So you know, in some sense, it's a free lunch. You know, at first we thought we had this trade-off that the more faster you want to grow, the more you want to have, the more inequality you're going to have. But this doesn't really follow from what we've got here. It doesn't. So we have the machinery if you're talking about people's decisions. I'd also like to have I mean, there's so many things you'd like to do, to be able to talk about decisions to go to school, which is, I think, the central one. In some sense, your schooling kind of dictates what kind of learning environment it is afterwards. I mean, those guys in the blue dots who didn't finish the 8th grade, they're not going to get jobs at Google, you know. So they've already made the decision about who they meet and interact with as soon as they dropped out of high school. My fourth topic My fourth topic is about international trade. There's a new paper by Alvarez Buera and myself. Applies the same idea of social learning, but there it's trade. In our model, trade affects who you're interacting with. You're going to learn from the people you're dealing with in the business world. But I don't want to start off on a new topic now. So why don't I just what I've really tried to do is to sort of show a particular style of matching up theory and evidence, trying to think about models which give you detailed predictions about the overall economy and about some features of the individual in that economy, and see how these models of this type how we want to match them up with actual data. And it's just getting going. There's a lot of people interested in this. A lot of things I would like to add. I'm working with Rossi Hansberg about what role firms, organizations play. They play no role in the examples I've just talked to you. There's a lot to be done, but I'm not going to do it today. So thanks for listening, and if you have any questions or comments, please do.
Thank you very much, Bob, for your brilliant presentation. So we're going to start now a few questions. Roberto, perhaps will be the first one. You want to ask a question? Oh, no.
He said that you come up here.
Oh, sorry. Question from the floor.
I left my clicker there.
So let me start. While you're thinking about your question, let me start with one. Perhaps I'm getting old and tired also, like Bob Gordon, but I don't want to go as far as him, saying that we entering perhaps just the slower productivity that you had, growth that you had in the last few years, just episodic, right? But don't think if you put in your model also schooling, is a possibility, for example, of how much the brain can take, how many people can get a PhD, how useful it is. Because if you take schooling, people getting more and more educated, right? First, and then high school, you cannot have everybody in high school, and college even less. And then it looks like you get I know that your concept of learning is much broader than just schooling. But isn't that a possibility, at least, I mean, to reach a...
That's a good question. That's a good question. And there are reasons why I sort of talked around the issues of schooling in my talk. And maybe Aloysio's seized on what all the examples I've given here are balanced growth path examples where relative positions don't change and everybody's growing at the same constant rate. If you want to incorporate schooling into a model like that, you'd want to have along a balanced growth path, everyone is going to split their time between schooling and working in the same way. So the fraction of people attaining each level of schooling is going to be a constant over time along a balanced growth path. And maybe that's what Aloysio was asking about. Now, a problem with that is that in the last, I talked about the last century and a half of U.S. history, but that doesn't work for schooling. People are getting a lot more schooling in the United States now than we were 100 years ago. That's so a theory of schooling is going to have to face up to that, and it's going to have the math that's going to do it is going to be it's not going to be the math I showed you today, because because there's some non-balanced growth path there. Now, you know, a lot of people recognize that. It's just kind of an unresolved problem. There's a nice book by Claudia Golden and Larry Katz called "The Race Between Technology and Education." That gives the data that you'd want to use for that. Now, whether this is the same as Gordon's question, or we're going to run out of potential ideas, I don't know. The models I'm talking about here is not going to. We'd have to have some typology of different kinds of knowledge, or something. But the model I've looked at today is too homogeneous for that. But I don't know. So far, so good. You know, maybe that's the way. We've been going at this 2% year. People come up with new ideas. They're none of the things that Gordon would like. Gordon's thinking about how things have changed since he was a kid. So for him, Facebook and Twitter are nothing. Who needs it? I mean, I don't need it. I've paid no attention to, you know what I mean? But my granddaughters are into it every day, and that's GDP. Those guys are producing goods and services.
But how about this argument that it takes big investment, share of GDP to get slower growth? I don't know if you've seen this type of...
I mean, I don't think the physical technology of Twitter or something like that is any big deal, is it? Google was a breakthrough. I mean, there's always... I don't know. If you'd asked me or Gordon to predict any of this stuff back when we started out in the 60s, you know, we'd been wrong on every detail. You know, these are creative people are going to come up with stuff you never thought of before. You couldn't have predicted the Beatles or something like that when you were listening to the music I was listening to in the 50s. You know, it's just creative people are always going to come along and surprise you, and we love it. We love hearing new music, new ideas, new entertainments. It's not just a question of flush toilets, although, you know, they're nice to have too. But that's what Gordon's talking about. But okay, we got that one down, so we can't do that again.
I remember when we had Edward Prescott here, and he quoted Einstein. He said, "There are things that count, but we do not know how to count." If I try to fit your model to the two Koreas after the war, or to the two Germanys, there are some factors which are not included in the model. The question is, would that be institutions? Would institutions be a subject in economics that fits this saying of Einstein?
To me, institutions is just a word for something you don't understand the forces involved. Like so many words people use in economics, they sound like they're words about something they know, but they're basically confessions that they don't know. So when we say there was a meltdown of the U.S. economy in 2008, have we learned something? Well, I don't know. I mean, you tell me what a meltdown is and give me a model that tells me what, I mean, you know, they're just words. So I'm not into institutions here. I don't think, of course it matters if you have a government that's, you know, stealing everybody blind or chopping people's hands off if they don't do the right thing. It's not going to help GDP. I mean, everybody knows that. But do we know when it comes about or not? Now, in terms of Korea and Germany, I wrote down balanced growth paths. That's a long-run concept, and it worked well for the United States, but not right after the war. But I think if you started, you can get some transition dynamics. out of a model like this if you set it up the right way. Where and Alvarez and I have some, not very good. But so I don't think there's anything inconsistent between catching up growth and the model I've written down. But
the parameters would be different in East Germany and West Germany and South Korea, North Korea, something like that. In the long run, steady state.
You have a different in ways that I think are discussable within a model of this type. Okay, so when Germany was unified, a lot of people in the backward East are now interacting in a serious way with joint business transactions and so on with people in the West, and they're upgrading their skills and knowledge, tremendously. So in terms of this, what I call social learning, people in East Germany have a much richer intellectual environment now than they did back when the only people they could talk to were each other and the Russians. And so I don't think that's. I think South Korea, once you remove the shackles of the Japanese occupation and let Korea operate on its own and with the military stuff resolved, they interacted hugely with American and Japanese businessmen, scholars, whatever. So there's a huge amount of learning from other people. So that wasn't something I talked about today, but it's certainly not inconsistent with the kind of model I've been talking about. I think on the other hand, I think that the kind of model I'm trying to think about is going to be a good way to talk about exactly those issues.
Okay, Fernando Lana.
I'd like to ask a simple question. In steady state, your model depends on two parameters, alpha and theta. Alpha is the rate of meeting people, and theta is the variance of the ideas. So, if I have open versus a closed economy, I would say that alpha would increase because the open economy, you are going to meet more people. But the second point is about theta. Theta is related to the variance of log earnings.
Yeah.
So if you have a more, let's say, an equal society where the variance of earnings is much higher than the other society, you would predict that this more unequal society would go in steady state more than the more equal society.
Let's go pretty much beyond. Let me talk a little bit about the work with Alvarez and Guerra, okay? Because we're thinking of a bunch of countries with maybe different parameters, theta, maybe different parameters for the level of income, and working them out under autarky, and now asking what happens if they start trading. And for us, trading means that you're meeting people who sell in your country, whether they're foreigners or domestics. So opening to trade means you're meeting people you didn't meet before. It's changing your intellectual environment. Now, if countries have different theta values, this tail parameter is crucial. Then, as soon as any trade occurs, anything else, you've all got the same theta. You've all got the same potential. Because everybody's got the same potential to get out there and find the best in the world, as opposed to just the best in your country. So now we got a world in which everyone has the same theta in the sense of long-run potential, and their current levels of production are small, so there's to be a catch-up growth thing. It would be unlike what Rubens and I were just talking about. I think those things are discussable within the context of this model, but I didn't discuss them today.
Okay, anyone?
Is that a?
There is a microphone.
I want to know if he is happy with that answer.
You want to continue your question?
So in your model, if like a high school dropout meets a PhD, he becomes a PhD immediately, right?
Yeah.
So don't you think like you need some similarity to really acquire knowledge from someone else, and that would make maybe the relationship with
Yeah.
like the variance not so big as you get in your model.
It's
a follow-up related.
Oh.
Can you do the increase in knowledge using a convex function between z and z prime, and as you acquire knowledge from z prime when z prime is greater than z, and can you close the model doing this? Because I don't think that you acquire immediately the same knowledge, but I think that when you interact with someone smarter than you can learn something. Can you do an adaptation to your model? Does this matter to your results?
Mo and I have some experiments of this type. What he's saying, let me just, it seems, Z is my knowledge, I meet Z prime, now if it's bigger than, I just absorb it. Now you kind of think that you got to be reasonably close to this guy in order to absorb his knowledge. So if I meet some physicist, I'm just too far away from, my physics is too far away from a real physicist for me to absorb that stuff. That doesn't work. So you might think that maybe I get to go, you know, a third of the way or something. That's that really blows this equation that I took from Corda. It's easy to describe it, but it changes the math enough so that most of the examples I gave today wouldn't fly. Now with Mo, we had the thing, it's all numerical, and we tried some stuff like local, that you can only learn from local people that are similar, not too far from you, and you know, it makes a big difference. There's no question. For example, in this social mobility thing, there's a lot of social mobility in my model. That's why the value Lorenz curves were real different from the earnings Lorenz curves. But that's also because, you know, if you're unemployed, working full time, you don't know anything, you got just as much chance of meeting some genius out there as somebody who's, you know, who's, everybody's got the same shot at absorbing new data as everybody else does. So it seems a little, and when you start modifying the model to take it into account, you lose a lot of the mobility, for example. So that made us think, Maul and I anyway, thought we better not claim too much about these Lorenz curves, because we know that by fiddling with the model in these directions, you can change it quite a bit. Yeah, we don't. Yeah, what you guys are hitting on is I wanted to write down an equation for the evolution of the distribution of knowledge, and we picked one that was really convenient in many ways, and you start moving away from that, a lot of stuff happens, and we really don't know very much about the technology of learning. I mean, it's really, you know, it's a substantive question, but there's
Okay,
a lot to be done.
Any more question? No, first him and then you. Okay. Because no, first him and then. Oh.
So we have a few other theories relating knowledge and growth. And
You're
they're
not coming
basi-
through on your.
Okay, so we have another few theories relating knowledge and growth, and they basically rely on either variety of inputs or expanding the technological frontier one step at a time. So those theories, basically, they emphasize the role of expanding this frontier of ideas. And yours is more about the propagation. It's basically focusing on the propagation of ideas. So how do you think we could try to distinguish empirical predictions of these potentially competing theories?
So can you tell me about which papers you're thinking about?
I'm thinking about kind of a quality ladder model in which you would just move one step of a time, but
Okay.
we wouldn't have a clear kind of limiting frontier of quality
Okay.
or TFP or.
So
something like that.
Arrow's 62 paper would be in your category, and so would Stokey's. It was kind of a quality ladder model.
Another one in which you basically introduce another input, and because there's some gains of having more inputs, you expand TFP again. So those are models in which you typically, propagation is very simple. You just get everything that's out there, or you get the latest one. So they are not focused on propagation that much, but they are more about not having the shortcoming of there's a clear limit of the best idea out there. So how do you think we could kind of combine them and try to distinguish the different channels or other ideas like that?
Yeah, that's a pretty good question. There's been a lot of work done on like patent races. You get some data, you get some interesting, head-to-head battles between two different firms. It's kind of neat stuff. To me, it doesn't potentially tell us much about economies as a whole, aggregate stuff. So I don't think patents are that important. Well, obviously for some industries they're everything, but in the overall economy, I don't think intellectual capital is that big a deal. Particular combinations of ideas, that's what we all think it really works. But is there going to be some abstract way of writing it? I mean, Jovanovic has done some nice stuff on this. There's a lot of things you could do. It's a big topic. Whenever I get too much into diverse inputs, diverse types of learning, diverse categories, I sort of realize I'm never going to be able to work out the general equilibrium without some symmetry or something that basically reduces it back to something. You know what I'm saying? This is the way economics works. You can't have one economic model for everything. You got to have some particular questions. I think I can deal with the German reunification with this kind of model. But I talk about some things. The stuff that Alvarez and Boyer and I are doing, the catch-up growth is too fast. The East and West Germany would be at the same level right away, but I don't know what to say. There's a lot of possible models out there. I don't think looking for descriptive realism is the way to go, but maybe that's not what you're saying either.
Okay, Isma.
Well, Professor, I'd like first of all congratulate you with this brilliant speech. And if naturally, with this model, we are excited because we'd like to know all about it and much more. So there are many details we would like to look for. I have three doubts. One is, how do you define the quality of the intellectual environment? What's exactly that? Because you're speaking about a mix of entrepreneurs with academicians, with the faculty members, with the public policy makers. What's a real quality of intellectual advanced environment? Which is the benchmark you're saying? The second point is related about people. Your model studies data from the year 1990. But we nowadays can see that in the world many countries are getting older and older. People are getting very older. So instead of having a pyramid in the demographic stage, we have many times barrels as a format. Would this format, this new older stage of people in many countries affect your model and the graphs you showed? And third point, people would like to have net present values a very high level, but many times they are affected by huge taxes, enormous taxes. The Brazilian case is evident. Given the high burden of the taxes, instead of even creating patents and intellectual powers in the country, inventors are remitting their inventions to Panama, to Luxembourg, etc. So to paradises, to fiscal paradises, because there they can make gains, and here they will make losses.
Yeah. I mean, everything you mentioned is interesting and important. The demography one, I think the countries like Japan that are just reproducing their own population are closer to fitting my model than the U.S. reality, which is all kinds of people coming in from abroad, which is just such a huge factor for us. I mean, you look at my collaborators, and not one of them is an American. I hardly ever see. That's the way economics is in the States now. But you know, I don't know how big those things are in terms of overall. I'm just trying to get a decently picture of long-run growth, and I'd like to get a decent picture of catch-up growth. Or the other things, you can't do everything in one model. I don't think.
Any more questions?
Yeah.
I was concerned about you get a good result, good empirical result, I think, when you show. Are you hearing me?
No, can't hear you.
I think you get a very good empirical result when you show the fitting with the model and the points. I'd like to know if you have alternative interpretations of the model. I mean, you think about knowledge being passed through people, but perhaps you can just think about better opportunities. So how do you differentiate between alternatives, interpretations of the model, the baseline model?
I mean, that's just a generic question. You can ask it about anything. I never had a model that could spell out the forces of earnings growth in an explicit way that matched up with data as well as I got there. So it's not like there's 16 different options, and I had 0 a few years ago, and now I got 1. That's how I view it. Now I'm taking a sort of high road in what I call a theory. You could see Jacob Mincer just fit a quadratic equation by running regressions to the age earnings profiles back in the 50s, and it worked like a dream. Now people have added third and fourth moments, you know. So that kind of curve fitting, everyone's noticed this pattern in the age earnings profiles, and you can just fit a curve to it. But when I'm talking about a model that kind of illuminates the forces that lead to a certain shape, to me that's just a theory at a different and more a different level. And at a helpful level. I mean, it's progress, I think.
Yeah, sorry. Perhaps I was my bad speech. What I mean is, your model, I think it's good because of that. I'm not just feeding the data, you know. But the question is, why to interpret the model as a learning history instead of another history, perhaps? It's the same model, as you
take it. But instead of have learning, you have just new opportunities. I mean, I think you can perhaps interpret like that, and what the difference between the two interpretations of your model, not of the data, no?
Are you talking about some distinction between innovation and imitation? There's a nice paper by Urzo Lutmer. I said in my setup, the initial distribution of knowledge has to include all the stuff that anyone's ever going to know from day one. You can't. Now, what Lutmer does is take a model similar to mine, but he in his model, you can have a bounded support for that initial distribution. So there's a best idea that's available at t equals 0, but then so that model in my setup, everybody would just pile up on that upper limit, and the growth rate would have to go down to 0. Now Urzo then adds to that model a kind of a Brownian motion luck feature that when you get a draw, you don't a draw from a guy, you get what you drew plus or minus some shock, which could be positive. So you can get lucky. So that means that in his model, that finite support keeps getting pushed out by lucky draws, and so the fat tail kind of grows. You know, the tail of the model, which has to be there initially in my setup, it kind of grows. It grows ahead of you. It seems like an easier, a more attractive description of how things really work. But the predictions of Lutmer's model are exactly the same as the predictions of my model. So they're in terms of the kind of data I just showed you. So observationally, it just seems, if they're observationally equivalent, I chose the simpler one. But Lutmer's, I learned a lot from Lutmer's paper too, let me tell you. So that's...
Okay, you have time for the last question, if somebody has. Okay, if not, I want to thank Vale again for making this puzzle, and for Bob Lucas for his brilliant presentation.